All right, good afternoon.
Good afternoon.
Good afternoon, sir.
Hope, hope everyone's doing well. My Novocaine from the dentist has finally worn off, so I can talk normally now, unlike my morning classes. All right, I would like to go over Cartesian products and tuples and functions and summations and matrices today. I haven't done attendance yet. I think only half the class is here, so I'll be nice and wait a few minutes. So any questions before we jump into all of that?
Well, I have a question from the 224 class. How do you read a character for like C and U?
You can just say read space variable name, and it will read whatever the person types.
Not only integers, but also like characters as well.
Yeah, whatever they type will go into your variable.
Oh, okay.
We love to help in the Discord if you want to ask us.
Yeah, that too.
Yeah, I did ask, but nobody replied. That's alright though.
Okay.
Sorry about that.
That's okay. Other questions? All right. Let's talk about Cartesian products and tuples. And we touched on this really briefly the other day, but it is one of the homework questions, so let's make this a little more formal. So a tuple is an ordered collection. And it's written inside parentheses instead of brackets to distinguish it from a set. So for example, parentheses 1 comma 2, that's an example of a tuple. Because it's ordered, it's totally fine if both of the things in the set are the same, because this is different from that. This is the first thing in the tuple, this is the second, right? So they're distinct. We could have, a 3 tuple, which is an ordered collection of 3 things. You can have an n tuple in general. A kind of quintessential instance of tuples are coordinates. If you think of Cartesian coordinates on a plane, every point can be associated with a tuple. It's a pair of numbers x and y, which correspond to how far over and how far up you move from an origin to get to that point. If you have a point in a 3-dimensional space, that's a 3 tuple. If you're in a 5-dimensional space, it would be a 5 tuple. So that's different from a set. Okay, it's an ordered thing. There's a first and a second. But they come up in set theory when we talk about Cartesian products. So let me give you the simple view of this first, and then we'll make it confusing and formal. But let A be, I don't know, a set containing a 1 and a 2 and a 3. And let B be a set containing an A and a K. Okay, if I define the Cartesian product, A times B, it's a set, so it's going to go inside curly brackets. But each element of the set is a tuple. And it's a tuple where the first element comes from A and the second element comes from set B. I shouldn't have called this an A, because that's going to get confusing. Let me call it H and K, like Hello Kitty. So the first element of our tuple comes from A. So for example, 1, the second element comes from B, for example, H. So 1 comma H is a tuple that's part of this product. Same with 1 comma K. Same with 2 comma H. and 2 comma k and 3 comma h and 3 comma k. And those are all the tuples we can form by taking, first element from A, second element from B. So that collection of 6 tuples, that is the set A cross B, Cartesian product of A and B. So it's all combinations of one thing from here and one thing from there. And so in general, A cross B equals the set of all tuples of the form A comma B such that little a is in set A and little b is in set B. So that's the more formal way to write it very precisely. So someone asked in chat, what would B cross A be? Well, it's the set of all tuples where the first element of the tuple comes from set B and the second element comes from set A. And we don't have to go very far to see that, there's one element here, h comma 1, and we don't find that element anywhere in here. So in this case, A times B is not the same as B times A. In fact, none of the elements in here are going to be in there and vice versa. They're going to be what we call disjoint sets. The intersection is going to be 0.
So basically, if it's A times B in all of the tuples in that set, A is going to come as the first element of the tuple.
Mm-hmm.
So Cartesian products are not commutative, right?
That's correct.
Okay.
Yep, you got it. And a little bit of oddity of notation, if we had 3 sets, and we do A times B times C, we're going to define that as a set of 3 tuples in sort of the obvious way. Now, if I just do A cross B, I'm going to get a set of tuples. And if I take that set and I cross it with C, I'm going to get, tuples that contain an element of C and a tuple from here. But usually when we want a Cartesian product of 3 things, we just write a set of 3 tuples. And it's a little easier. And it's basically equivalent to if we did, A cross B and then did cross C. All right, I did not do an attendance ping yet, but I will do one right now. So go ahead and send me a note. Canvas name dash here, please.
You said that it would be basically the same as if you did it separately. But what's the process of taking this information and sticking in the tuples? Because from my perspective, you did A cross C and then A cross B, they would result in separate sets.
Yeah, so this is kind of the definition of a Cartesian product of 3 sets. And if we did 4 sets, we would get a set of 4 tuples. Technically, if we did this, right, this would be the set of all A comma B comma C, where A is from A, B is from B, and C is from C, because the elements of A cross B is a set of tuples, and the elements of C are C, and so this would be a set of 2 tuples, where the first element is a 2 tuple coming from A and B, and so on, and you get into lots of irritating parentheses and so on. So even though if we did this in parts, if we did A cross B and then we cross that with C, right, for working purposes, if you want the Cartesian product of 3 things, write a set of 3 tuples.
So basically, it's just close enough that we drop the parentheses to save standing.
Yeah, yeah. And we could mathematically define a one-to-one mapping between these things and those things. And so whatever properties, apply to this set will also apply to that set. So we usually just write 3 tuples if it's 3 sets we're multiplying and so on.
So basically, A times B times C is equivalent to the quantity of A times B times C, right? You can just drop those parentheses?
Yeah, I don't want to make this more confusing because I'm trying to make it less confusing by doing this.
Okay.
Let's do a specific example though. So let A equal 1, 2. Let B equal 3, 4. Let C equal 5, 6. So A cross B is going to have 4 elements. Alright, so first element comes from A, second element comes from B. If I were to take A cross B and cross that with C, I'm going to get a set of tuples. The first element's going to come from A cross B, so it would be something like 1, 3, and the second element comes from B. So we get things like this. If we just, letter of the law, right, this is A cross B, so if we take that and we cross it with C, this is what we would get, right? That's confusing to write. So when we start off and we just say we want A cross B cross C, we're going to write that as this. Right it as a set of 3 tuples. Is there a type of set where the set doesn't exist with the prerequisites? Like as an example, chocolate milk. You can have milk by itself as a beverage, but chocolate is not necessarily a beverage without being combined with the milk. Oh, interesting. I have to think about that. It's an interesting question. That's a question posted in chat if people want to read it.
We kind of covered that with like desserts and vegetables, carrot cake and rhubarb pie.
Yeah, when we were doing Venn diagrams. But I think there's a different aspect of that being asked here.
I actually can't understand the question.
Oh, I think it's a little bit about something that in some sense doesn't make sense unless it's combined with something else.
Well, they do kind of compare. They are both edible.
Mm-hmm. But not beverages. Yeah, let me think about that, and maybe if you can come up with a different way to ask it, or send me a note and we can talk about it in email maybe. All right, let's move on to functions. So suppose we have 2 sets. We have a set D, and we have a set C. So we can define a function named f, and we usually write f colon one set arrow another set. and this is a mapping or an assignment of an element D, an element C contained in this set C, which we write as, an assignment of an element C in C for each element D in set D. So a function is an association or an assignment of an element over here for each element there. So if F maps D to C, we say F of D is equal to C. So here's some point D, here's some point C, here's our function F. So it's just a collection of these assignments, right? It's saying, well, if you look at this point D, I'm going to associate that with this point C. If you look at this point, I'm going to associate that with this point. So if you make such an association for every point in D, then F is a function. And in this case, it's going from this set to that set.
Is this one-to-one, or can it kind of like compress?
So this is the only requirement for it to be a function. It has to take each point here to a point there. But we can talk about types of functions, including one-to-one and surjective and bijective, and we'll get to that shortly. But to be a function, all we require is that each point here maps to some point over here. Now, if there's a point hanging out over here on the edge, and F does not associate that to anything in C, it's no longer a function. If it associated this to something that wasn't an element of C, that would not be a function. And if it associated a point to more than one thing in C, it would not be a function.
So the whole purpose of function is, in terms of sets, is just to map things from one set to another set.
That's it.
Okay.
A question, if there's more elements in C than there is in D, is it still a function? Like if all the elements in D map to something, but not all the elements in C are mapped?
Yeah, I could have a bunch of elements out here that aren't mapped from anything. That's totally fine. It's still a function. The only requirement is for each element in D, right? We associate an element of C. So everything in here has to be mapped, but there can be extra stuff over here that's not mapped. That's totally fine.
Okay.
We could also have things over here that map to the same element. That's totally fine. That's still a function. And these are the same functions you study in math classes, right? It's exactly the same thing. And this business of not being allowed to have one point mapped to two things, that's your vertical line test from math class, right? So like, y equals sine of x. Well, whatever x you put, you can only get one value of y out, right? There's multiple x's that take you to the same y. That's okay. But you can't say, well, the sine of x is both, 0.2 and 0.3, right? It can't have two function values. That's the idea of only mapping to one point. All right, so we can specify functions a number of different ways. So we can draw pictures, right, like this. That's not a very good explanation of what this function is, but we can draw a picture like that. We can make a table. I suppose that f goes from the set 1, 2, 3 and into the set of all integers. So I could say if x is 1, f of x is 17. If x is 2, f of x is negative 5. And if x is 3, f of x is 148. There's a definition of my function f. And it goes from the set 1, 2, 3 to the set of all integers. That's a perfectly valid function. We can also represent functions with equations. We could say, for example, f of x goes from the integers to the integers, and it's defined by an equation, f of x equals x plus 5. So now I'm associating with every element of this set an element of that set. What's the association? Well, if I pick the number 0, I'm going to associate 0 plus 5 is 5. So my function would take 0 to a 5. If I pick the number 1, my function would take the number 1 to 1 plus 5 is 6. We can also represent functions with code. We can write a function in C, and what does it do? It takes an argument of some type. If we say integer x, it comes from the set of integers. If we say double x, it comes from the set of real numbers. If we say char x, it comes from the set of characters, and so on. And it maps for each thing that you can feed it some value in an output set. In this case, the set of integers, but it could be, you know, reals or something else, floats, doubles. Right? And that's a code version of this idea of a function. So we've known about functions for some time, right? We encounter them in multiple math classes, but from set theory, we can just think of it as a mapping from one set to another. We can also represent functions as a set of tuples. So, well, let me go back to this function here, this f of x. I could write the following set. All right, there's a set of 3 tuples, and this corresponds exactly to that function. How do I get the function out of this set? Well, if I want to know what f carries something to, I find a tuple where the first element is the thing that I want to map, and the second element of that tuple is the thing it maps to. So what is f of 3? Well, there's a tuple with 3. The second element's 148. This is telling me that f carries 3 to 148. That's what that piece of information says also. So any function can be associated with a, or for any function we can associate a set of ordered tuples. So suppose we have some function of real numbers. So this is like every function you've ever studied in math class, right? Exponentials, trigonometric functions, polynomials, right? They're all basically functions from reals to reals. Logarithms, you can't have a negative number or a 0, but you know, sines, cosines, things like that. So any particular function f we could associate as a set of tuples where the first number and second number come from the set of reals. Well, carry that a little further, right? For a particular function, there is a unique collection of tuples, pairs of real numbers, corresponding to that function. So if we thought about all the sets of tuples whose elements come from the reals, right? any function corresponds to one of those, one subset of that collection of tuples. So if I take the Cartesian product of the reals with itself, and I take the power set of that, this is a big set, right? This is all the ordered pairs of real numbers. And the power set says, give me all possible subsets of that set of ordered pairs. Well, this set right here, this contains every mathematical function from reals to reals. Including, you know, this little weird function right here. Well, this is a subset of that. And so this set that corresponds to this weird function that I just pulled off the top of my head, that set is contained in this set, the power set of R cross R. So a handful of symbols, right, script P, R cross R in parentheses. Right here I've defined every mathematical function that we could ever think of, from the real numbers to the real numbers.
One argument and one output, right? Okay.
Yeah, with one input, one output. Another way to think about this, if you want to extend this, right? R cross R, well, any point in here, any member of R cross R is just a tuple, a pair of real numbers. Well, a pair of real numbers, we can just think of that as a point on the xy axis. So every element of this corresponds to a point. So a subset of R cross R is just a subset of points. And every function can be associated with a subset of points on the xy axis, in particular its graph. So if I...
R cross R would be on like the z-axis?
So that would be, yeah, that would be a curve in three-dimensional space. So say a function that takes two inputs and generates one output.
So relating this to computer science,
Mm-hmm.
this would be super useful if we had some function with a single input and output. We needed to know all possible things we could do with that function.
Mm-hmm.
Okay.
It may not be practical, but it's definitely useful in some sense. All right, so let's come back a little closer to reality, and let's talk about types of functions. All right, so there's going to be some terminology here, and these can be confusing if I don't do a good job when I describe them. But the concepts, trust me, are easier than the explanation of the concepts. Let's put it that way. So let's have a function f from A to B. Okay, the set A that f maps from, this is called the domain. And the set B that it maps to, this is called the codomain. And if we have some element A contained in set A, we can say f of A is the image of A. So we can think of a function almost as like a projector. You shine it through the set A and you get a set of weird projections on the wall that are how that function transforms each point in A. So we call it sometimes the image of A. And sometimes we just say F maps A to B. Okay, so suppose F goes from A to B, and suppose G also goes from A to B. We can say that F equals G if f of a equals g of a for all elements in set A. So for two functions to be equal, they have to agree everywhere, basically, which is not too startling. We can also compose functions. So suppose f goes from a to b, and g goes from b to c. We could think of something like this. Right, we could say g of f of a. And so f carries a to some point in B, and G will take every point in B and carry it to some point in C. And so for any A, we could find what G of f of A is, so we can use this symbol. Let me draw that a little more carefully. This is called composition. So G composed with f is a function that goes from A to C. And it just means, you know, if you want to find G composed with f of A, just means first take f of A, and whatever you get from that, now take G of that. So it's a way to put functions together. So for example, and let's just go from reals to reals because it saves us having to think too hard. So suppose f of x equals x squared, and suppose g of x equals x plus 1. So g of f of x would say you're going to take some number x, we're going to apply f, which is going to square it, and then we're going to add 1. On the other hand, f of g of x says we're going to take some number x, we're going to apply g to it, which is going to change it into x plus 1. And then whatever g gave us, we're going to apply f to that. So we're going to take x plus 1, and we're going to square it. So f of g would be x squared plus 2x plus 1, whereas g of f would be x squared plus 1. So we can do compositions like that. It's a little linear algebra-ish, and other stuff we do in here will definitely harken to linear algebra. So if you've done linear, some of this will be familiar. If you haven't, you'll look back on this when you get to linear. If you're taking linear this quarter, these two play together really nicely. So it's a fun combination of topics. Alright, so I said I was going to talk about types of functions, and I branched off into functions on operations on functions. So types of functions. 3 categorizations. So again, we're going to do f goes from A to B. So first one is surjective. Which we also call onto. If it maps to all of B. So remember, we said originally it's totally okay if your function doesn't map to everything. We can have some points out here that aren't mapped. It's still a valid function. But if it also maps to every single point over here, then we say the function is surjective. So surjective if it maps to everything on the right-hand side, everything in the codomain. Otherwise, it's not surjective.
So it's like a one-to-one function, basically.
Not exactly. It's really just saying that everything is mapped to. But for example, I can, make this thing surjective. If that's all that's in C, now this is a surjective function. But it's not one-to-one because this point and this point both map to the same point over here. So it's onto or surjective, but it's not one-to-one. So one-to-one, which we also call injective, F is injective if it maps different A1, A2 to different points in B. So picture is certainly worth 1,000 words. If these are all the points in A and these are all the points in B, this is surjective because everything over here is mapped to. It's also injective because different points here map to different points there. If there's an extra point over here that's not mapped, it's no longer a surjective function. And if there was a second point here that mapped, say, to the same point as this one, now it's no longer injective. Alright, so surjective means it maps to everything. Injective means different things here always map to different things there.
What if a function maps to nothing?
The only way it could be a function and not map to anything is if A is the empty set. Because to be a function, everything in this set, the domain, has to map somewhere.
Okay.
So injective is kind of like no redefining or no like double definition. It'd be like every element in A has a unique spot in B.
Right, right.
An example, like I said, that is injective would be like x to the power of 2, yeah?
Yeah, so if f of x equals x squared, let's do f from the reals to the reals. So f of x equals x squared. Is this surjective?
It wouldn't be because it wouldn't be mapping to any negative numbers.
Right, so to be surjective, we need to know that for any number we pick over here, there's something that maps to it. In other words, there's for any number, there is something whose square is equal to that. Which is the same as saying every number has a square root, and that's not true. There's no value over here that when we square it will give us -1. So it's not surjective. Is it injective? Do different values here always take you to different values over there?
Also no, because negative numbers map to positive numbers. Oh, you have like -2 maps to 4, 2 maps to 4.
Yeah, exactly. So f of 2 would be 4, f of -2 would also be 4. So we have two different things, two different A1, A2 that map to the same point, so it's not injective either. On the other hand, a function like f of x equals x plus 1, that is surjective and it's also injective. And so f is bijective.
The value will always be different, right? It's never going to be the same number.
Yeah, so we can actually prove both of those points. So if I pick some value over here, 17, can I find an x that maps to it? Yeah, all I have to do is subtract 1. F of 16 will be 17. So that tells me that it's surjective, that for any value over here I can find something that when you add 1 gives you that value. And to show that it's injective, I need to show that if I have two different points over here, they map to different points over there. Well, you know, f of a1 is a1 plus 1, f of a2 is a2 plus 1, the only way that these can be equal to each other, the only way a1 plus 1 can equal a2 plus 1, is if a1 equals a2 plus 1 minus 1, which is a2. I gotta have a1 and a2 equal to each other. So if a1 and a2 are different, we've just shown that they will map to different points. So that makes this injective as well as surjective. And so in that case, we call it bijective. And we say it's one-to-one and onto if it's injective and surjective. All right, so we can write this mathematically. Suppose f goes from A to B. F is surjective if for all B in the set B there exists an A in the set A such that f of A equals B. So f is surjective if for any value that we pick out of this set B, there's some value in A that maps to it. And if f is injective if whenever A1 is not equal to A2, then f of A1 is not equal to f of A2. So that's saying it takes things to different points. All right, making some sense? So we've got pictures, we've got words, we've got mathematics. What's left? Cake theory. So if this works for you, super. If not, don't worry about it. But I like to think of this in terms of a function which goes from a set of people to pieces of cake. All right, you got a set of people, you got a table with a bunch of pieces of cake cut, and f is our function that basically for each person says, hey, which piece of cake do you get? All right. So what does it mean if f is surjective in sort of the life and times of the people and the pieces of cake? What would it mean to say f is surjective?
It would be if the entire cake is like divvied out.
Yep. So whole cake.
Or leftovers.
Whole cake is eaten. No leftovers. I hear a cappuccino.
Then like F is bijective. The whole cake gets eaten, but everybody gets a different piece of the cake.
Yeah, let's do injective first. But I think you're right on bijective. But what does injective mean?
Everyone gets one piece.
Yeah. So injective means everyone gets their own piece. You don't have two different people being assigned to the same piece of cake. And then bijective is just the two of those together, but in the life and times of people in cake, what that means is that each person gets one piece of cake exactly, and the entire cake gets eaten. Each person gets their own piece, and there's no leftovers. What can we say about the size of these two groups if we know that f is bijective?
Wouldn't they be equal in size?
Oh, thank you. Yeah, it means they have the same number of elements, right? If you have more people than you have pieces of cake, then people are going to have to share, right? And if you have more pieces of cake than people, then you're going to have cake left over, because a function can't map a person to two things, right? That's not a function. Vertical line test fails. So if it's going to be bijective, they're going to have the same number of things in each set. And for finite sets, that's a requirement for bijectivity. All right.
Can like more than one person get the same piece of cake though?
Sharing?
I guess.
So
Like, yes, the married couple share a piece because, I don't know, they're gross.
so it could be that, you know, f of one person goes to this piece of cake and f of another person goes to the same piece of cake. It's still a function, right? It's just not injective anymore. And what's happening here is, you know, here's the set of people, here's a set of cake slices, here's one person, and here's another person. And they're both mapping to the same piece. So it's a function, it's just not injective or one-to-one anymore. One-to-one means, you know, one thing here goes to one thing there. One thing here goes to one thing there.
It's just kind of being facetious
Mm-hmm.
and thinking about it in a reality sense.
Yeah. That's a useful way for me to think about things usually, is to try to tie them into something other than symbols and words. All right. So sets are powerful, right? Sets let us capture like everything there is to capture about functions in some sense. And all the functions that we talk about and learn about, all the functions that we write in our programming lives are really just subsets of the power set of, you know, some huge Cartesian product. So that's kind of cool. All right, summations. So we're kind of into review territory now, where, you know, some of you have probably seen some of this. A few of you may have seen all of it. A few of you may have seen none of it. Where we're just kind of like going over the building blocks we're going to use. So a lot of times in discrete structures, you know, where we're dealing with integers, we're going to talk about things like, you know, some function of 1, and we want to add f of 1, f of 2, all the way up to, say, f of 10. And rather than write all this out, we have a shorthand notation. So we write a sigma, a sum notation, and we could say something like I equals 1 to 10 f of I. And this means exactly the same thing as that. Just a more convenient way of writing it. So just like we did a union for a bunch of unions. And a couple of things to note here. First of all, this is like a for loop in programming. And we could set a sum, you know, a running sum to 0. And then we could say for I equals 1 to 10, sum equals sum plus f of I. And when we're done, sum would be the same value as this. Another thing to note is that just like in programming, the choice of variable is really irrelevant. If I do the sum from j equals 1 to 10 of f of j, I get the same value out, right? Just like if I write a for I equals 1 to 10 and I change the I to a j, as long as I change my i's to j's inside my loop, I'm going to get the same answer. I can also change my index. For example, if I said I want I to go from 2 to 11, and I want to add f of I minus 1, right? Well, how do I figure out what this sum is? I set I equal to 2, and I write this down, f of 2 minus 1. And then I set I equal to 3, and I write f of 3 minus 1, and so on. And I stop when I get up to I equals 11, and I write f of 11 minus 1, and I just add these all together. Well, that's just f of 1 plus f of 2 plus all the way up to f of 10. Now, I wouldn't normally change this into this, but if I started off with this, going from 2 to 11, maybe it's easier to think of it as something that goes from 1 to something, so I could rewrite this to look like that. And so maybe a more likely case would be if someone asks me to find this, well, I could change this around, and I could say I'm going to go from 1 to 10, and I'm going to do f of I plus 1. So when I is 1, I'll do f of 2. When I is 2, I'll do f of 3. When I gets to 10, I'll do f of 11. Exactly the same thing as that. But sometimes we have convenient formulas for simplifying summations from 1 to something. Not so much for 2 to something, so we could take this, rewrite it like that, and then maybe use some formula for a summation of this type and write it as a closed expression. Alright, we'll also see double summations. And these don't have to be any harder. So if you're faced with something like this, my suggestion, break it into pieces. This is the sum from I equals 1 to 3 of this, whatever this is. Right? Set I equal to 1, find this. Set I equal to 2, find this. Set I equal to 3, find this, and then add up those 3 things that you found. And you can do that a couple of different ways. One way would be to take this and figure out what this is first. Well, set j equal to 1. Set j equal to 2. Add those together. Well, now it's just a plain old summation. Sum from I equals 1 to 3 of this slightly more complex equation. So sometimes breaking things into pieces like that will make life a little easier. And then there's all sorts of niceties like this. If we have a summation and we multiply that sum by 5, we get the exact same thing as if we took the summation of this inner thing multiplied by 5. And things like this. Right? If we have 2 things that we're summing like this, we can also just take the sum of those 2 things added together, and we'll get the same value out in the end. You got a homework coming up in your next set of homeworks that I think lets you explore this stuff. Does this look familiar from something else in math?
It looks like calculus.
Yeah, this is analogous to formulas that you learn for dealing with Riemann sums, right? Integrals. You can break them apart like this. You can multiply by constants. You can pull constants out, and so on and so forth. Why does that work? Because an integral is just a summation, right? It's a summation where we happen to go up to a really big number, and we happen to be adding really tiny little things. But it's an abstraction of this notion of a straight summation. All right, let's take a 5-minute break, and then I'll make a few comments on matrices, which we don't do a lot of in this class, but I want to at least touch on them because they'll come up in graph theory later. Let's take a 5-minute break. We'll come back. We'll talk a little about matrices, and then if we have time, we'll talk about a couple of paradoxes in set theory. I'll do an attendance ping after we come back.
Chocolate.
Yeah.
Crystals.
Novocaine wore off about an hour ago. So that's good.
Oh, before you had to talk, that's good. Oh, I guess not.
No, I was talking with it. It was okay.
Really?
Yeah.
Can you hear it when they're recording?
Probably. He really nailed my jaw.
Maybe I traumatized
I
him.
think so. He just kept going. He's like, well, let's do a little more. And I'm like, hey.
Oh. Yeah.
So I tried to eat a little Debbie zebra cake, and I couldn't open my mouth far enough.
Yeah.
I'm getting there now.
Yeah.
Yeah. So, got a good temporary go back in November.
Oh, really? It's a temporary?
Yeah, because I have to, like, make the actual part.
Oh, right, right, right.
Yeah. That's usually pretty quick.
Yeah. How long do you need to?
About an hour.
That's not bad.
No, it's fast.
Yeah.
It's all just trembling, man.
Yeah. Yeah.
So we got to do the noiseless dental drill. Yeah. We do like a drill if I could make any noise.
You still feel it though.
It's the noise.
It's the pressure that gets me.
Really?
Yeah. I don't mind the noise.
That's what nobody thinks.
But even if you're numb, you can still feel like that's almost creepier.
Nothing as bad as the smell.
The taste is yeah, the taste.
Yeah, the
of,
taste is
yeah.
bad too.
I got a big old swallow of whatever the filling stuff was.
Yeah. Yeah, we can actually like see like the smoke and the flames and the people running away with their hair on fire. It's really bad. That's the other dentist. What am I doing time wise?
survive.
I got 33 seconds.
Well, we can have a full conversation.
Yeah. Alright, I am back. So let's go ahead and do matrices. And if you didn't just send me an attendance ping, go ahead and send me an attendance note. Let me know you're still here. And let's talk about matrices. So again, this is a linear algebra topic, but it comes up in other contexts depending on your 120 class. You may have encountered matrices when trying to solve KVL, KCL equations. Matrices can be used for solving simultaneous equations, and this is part of the subject of linear algebra. So we bump into these things over time. Let me just give you a quick overview of a few key points on matrices. So what is a matrix? It's just a bunch of numbers inside parentheses. That's my non-mathematical definition. So, 4, 3, -1, 6, there's a matrix. This is a 2 by 2 matrix. They don't have to be square. They could be, 10 by 2 or whatever. They could be 1 by 1, or they could be 1,000,000 by 1,000,000, right? So it's a two-dimensional collection of elements. You can have matrices. Usually our matrices are made up of real numbers, but it could be a matrix of integers, could be a matrix of smiley faces, could be anything. So we define multiplication on a matrix. So let me do something like this. There's another matrix B. So if we want to add these matrices together, we just add element by element. So A plus B would be 5, 5, 2, and 10. Right? Addition is straightforward. Multiplication gets tricky though. So when we want to do A times B, we do something funny. We take this first row and this first column, and we do what's called the dot product. We do 4 times 1, and we do 3 times 3, and we add them. And so this 4, goes here, and this is a 1, and this is a 3, and this is a 3. And that tells us what this first upper left element is. And when we want to find the second element, we would do the first row and the second column. And so this would be 4 times 2 plus 3 times 4. And so on. The details aren't important. We're not going to multiply matrices in this class. But there's a procedure you do. You do not just do 4 times 1, 3 times 2, -1 times 3, 6 times 4. That's not how matrices multiply. Right? We do this particular operation. And there's a few consequences of that. One consequence is that in general, the product of two matrices, and this is not a Cartesian product, it's the same symbol, but the product of two matrices is usually not the same if you switch the order of the matrices. In fact, a lot of times this is not even well defined for both orders. The dimensions of the matrix have to be set up just right for this to even make sense. There's also a particular matrix called the identity matrix, and if we're talking about 3 by 3 matrices, this is what the identity looks like. It's 1's going down a diagonal, 0's everywhere else. And the identity is called the identity because it acts kind of like a 1. For any matrix A, if you multiply by I, you just get back A. So it's like a 1, like a unit.
multiplication for a second?
Mm-hmm.
Okay, thank you.
Okay. So there's no division defined for matrices. There's no such thing as A divided by B. But what we can define is an inverse. So given A, if there's some matrix B such that A times B is the identity, in other words, if given a matrix you can multiply by something and get back to 1, then we say that B is the inverse of A. It's like the reciprocal. And so when we do arithmetic in school, if we want to, do something like 5 divided by 7, what do we do when we're first learning this? We take 5 and we multiply by the reciprocal of 7. So if we wanted to do A divided by, X, we could do A and we could multiply by the reciprocal of X, or what we call X inverse. I should have used something other than X. So finding inverses of matrices is a key to being able to do something like division. And in CSE120, right, we usually just use MATLAB or a calculator to find the inverse of a matrix, and we use that to solve our simultaneous equations. But let me just mention that this business of finding the inverse of a matrix, this is a big deal in computer science. It's a simple but computationally expensive operation. And in computer science, we're thinking about matrices on the order of, million by a million. So, how many elements is that? Well, 10 to the 12th. So 1 trillion elements, 8 bytes each, 8 trillion bytes of memory to store one of these things, right? Really, really expensive to do a lot of computation on these. If you can find a way to invert large matrices efficiently, you can sort of name your price. This is what fuels the engine of our world today, is being able to invert matrices, basically, because it lets us solve simultaneous equations. And this is where a lot of machine learning comes from. This is where a lot of the computer based things like portfolio management and things like that. So this is a big problem, and it's not bad to write a program to do this, but it ends up being really time consuming. And so that's an interesting question to explore. Yeah, I did an attendance ping, so if you missed it, go ahead and just send me a note right now saying you're here. All right, anything else I need to say on matrices? And the way we multiply matrices and the way we write their inverse and stuff boils down to doing a lot of summations, basically. And that's really where the expense of this comes from, right? When you do a double summation, you've got a pair of nested loops. If you do a triple summation, you've got a triple nested loop. And if each of those loops runs for 1,000 times, you've got 1,000 times 1,000 times 1,000. That's 1 billion iterations of your inner loop, and that's expensive. All right, so let's play around a little with some parting thoughts on set theory. There's some discussion on Discord over the weekend about George Cantor, and if you haven't read a biography or a Wikipedia blurb on George Cantor, give it a read. It's really interesting. So George Cantor is the person who showed that the set of reals was in some way bigger than the set of integers. This thing that we explored with Hilbert's Grand Hotel on Friday. So he came up with this result that the cardinality of the reals was strictly bigger than the cardinality of the integers. And you want to talk about upsetting people. People got really upset at this. And this poor guy got flack for the rest of his life for having come up with this result. And he was blacklisted from certain positions that he sought at universities. He was considered a heretic. He was the subject of all kinds of scathing reviews and criticisms from people because he had proven this result that didn't make intuitive sense to anyone. And mathematics is supposed to be kind of devoid of our own biases and preferences, and sort of get us closer to truth in a more pure sense. But the history of mathematics is filled with cases where, just like the Pythagoreans, they came up with this result that the square root of 2 was irrational, and it messed with their worldview, and so they didn't talk about that, and so George Cantor, came up with this result and caught a lot of flack for it, but it's a beautiful result nonetheless, and it's one that people seem to have finally made peace with. Yeah, that does seem like a common theme, right? Not just in mathematics either. But for me, I think it's particularly alarming in mathematics. So we'll go through a proof of this another time. I don't think we'll have time today, but let me show you something similar to this. This is something called Russell's paradox. I don't know if it's 1L or 2. I'll split the difference. So Russell's paradox is a question in set theory, and it's a very simple question to pose, and it's an interesting one to think about the answer of. So let me set this up for you, and this is going to be built around an idea of a set property. And this is the idea of a self-consuming sets. I knew I spelled that wrong. So let S be a set. S is called self-consuming if it contains itself. All right, what does this mean if a set contains itself? That's not possible, is it? It's hard to imagine a case. We know sets can contain other sets, right? I can have a set consisting of the set of integers and the set of reals. That's perfectly fine. So, there are sets that contain S, but is it possible that S actually contains itself? And if you think about it, it doesn't seem like that's possible, right? For example, my favorite set, my set of 2 pens. Well, does this contain a set of 2 pens? No, it contains a black pen and a silver pen. That's all that's in the set. There's no third element, which is a set of 2 pens, right? And if you think about this, it's hard to imagine how a set could be self-consuming. But we can, make whatever definitions we want. I can define Q to be the set of all cars that have 4 wheels on bottom and 2 wheels on top and cow horns coming out of the tailpipe, right? And as far as I know, there are no elements in that set, but I can still define that set, right? So a set is called self-consuming if it contains itself. So I'm going to make a new set. I'm going to say let do I want to call it B or G? I don't want to get this backwards on Nope, don't have it in my notes. Okay, I'm gonna have to fake it. Give me 1 sec. So I want B to be the collection of all sets let's see. That are not self-consuming. Okay, it's going to take all the sets that are not self-consuming and going to toss them into B. So what are some of the things we find in B? Well, certainly the set of integers, because the set of integers is not self-consuming. It doesn't contain any sets at all. It only contains integers. The set of reals is not self-consuming, so the set of reals will be in there. The set of 2 pens will also be in there because that's not a self-consuming set. So B is a really big set, right? It's got probably every set we can imagine. Every set we've talked about this course so far would end up being a member of B, because we haven't talked about any sets that contain themselves. Okay, so here's the question. Does B contain a copy of itself? In other words, is the set B itself self-consuming?
Can I propose we just don't ask this question instead?
I already asked it, unfortunately.
This is the paradox of that, you know, it must contain B if B is not self-consuming, but as soon as it contains B, it is self-consuming.
So
it can't contain itself then.
So it can't contain itself, so it's not self-consuming, which means it would be an element of B, because B contains all the sets that are not self-consuming.
So there really is no right answer to that.
So there really is no right answer to this question. There's a paradox here. It's not that we can't answer the question, it's that whichever answer we provide, and the answer has to be yes or no, whichever answer we provide leads us to a fallacy, a contradiction, something ridiculous. And so that's called a paradox. And it's an indication that there is an inconsistency in our logic or our mathematics. And this is happening because we are allowing sets to be just arbitrary collections of things. This is what's called naive set theory, where you just say, you know, take a bunch of stuff, put it inside curly brackets, you got a set, right? And under that definition, I'm allowed to say, okay, B is, here's my curly brackets, here's the stuff I'm going to put in there, all the sets that are not self-consuming. And that is too loose a definition of a set to be able to develop mathematics on without creating contradictions and introducing paradoxes. So everybody see the trouble with this, right? If B is a member of itself, then it is self-consuming. But by construction, B only contains sets that are not self-consuming, so it cannot contain B. So if I say, yes, B is contained in B, I'm led to the conclusion B is not contained in B, and that's a contradiction. But if instead I say, okay, the answer is no, B is not contained in B, then B is not self-consuming, and according to this definition of B, it should contain a copy of it, because B is not self-consuming. So if B is not a member of B, B must be a member of B. And if B is a member of B, then it's not a member of B. In other words, if it's self-consuming, it's not, and if it's not, it is.
Couldn't that just kind of be solved by, like, having a rule defined for creating sets like this, that you, like, it should be written all sets that do not, or are not self-consuming and itself?
Yeah, so you need to add some stuff to this naive set theory to basically prevent you from doing this kind of thing. And so you go back to the drawing board and you create what's called axiomatic set theory. And you basically, just like geometry, you start with a set of axioms, things that you just accept as true. In geometry, what are our axioms? Parallel lines never meet, right? There's a unique line between any 2 points, things like that.
Perpendiculars are always at a 90.
Yeah, yeah. So we do the same thing for set theory. We come up with a set of axioms. And what axiom should we have for set theory? Well, that's something that was explored heavily in the beginning of the last century. And a version of axiomatic set theory called ZF was developed. Zermelo-Fraenkel. And it gives us a set theory that looks, exactly like the set theory we've been talking about, except that, there's more specifics on what can be a set. How do we make a set? It's not just any willy-nilly things that we want to throw inside curly brackets. There's another branch of set theory called ZFC. And it's like ZF, but they add one more axiom called C. And this is called the axiom of choice. And I'll tell you effectively what the axiom of choice is. Let me draw a set here. Let me show you a set here. So here's a set of 3 pens. If I asked you to pick one pen from that set, would you be able to do it?
Yes.
Sure, why not?
Yeah, if I said pick a pen, every one of you could, if you weren't on Zoom, could pick one of these pens, right? Can you prove that it's always possible to pick a pen from this set?
I'm going to say yes, because each element is distinct from the other elements.
Each element is distinct from the others, but how would you prove that it's possible to choose one?
The nature of them being independent elements. I mean, I thought the answer you just gave made intuitive sense.
So they are independent, and if I lay them out on a piece of paper, I could say, well, pick the pen on the left. Or I could say, pick the one that's shiniest. Or I could say, pick the one that's tallest, or the one with the most ink, or the one that's oldest, right? Because I know something about the nature of these pens, but now if I put down, a mouse and a phone, and I say, pick one of these elements, can you do that? Well, yeah, you and I can do that because we're human and we have free will and all this kind of stuff, but how can you prove that it's always possible to make a choice? And it turns out that's a really, really hard thing to prove. In fact, it cannot be proven, but it can be accepted as an axiom. That's what the axiom of choice is. Your wormhole for the day. If you choose to accept it, go ahead and Google axiom of choice and see where it takes you.
Can you prove? Could you possibly prove it if you had any strategy or system of chronology?
You could, and for particular sets, you can always find a choice function. Or I think most always. If you've got a bunch of positive integers, you could pick the smallest one. Or pick the first one that's prime or something like that, right? But to take an arbitrary set and be able to choose one element from that, we can't prove that that's doable. We can't prove that it's not doable. So there's an axiom.
Is it just because of how we define choosing? Because from my perspective, the idea that so long as we can differentiate the elements, they can be chosen.
That's from your and my perspective, because if someone says choose something, I'll just close my eyes and whatever one I grab, I'll choose that. But trying to make that formal is hard.
Yeah, actual the actual logical system, I guess that would define it. Kind of in order to make that choice, not just human intuitively, you kind of need an identifier for the pieces.
Yeah.
Identifying details, I guess.
Mm-hmm. And so a lot of proofs in set theory rely implicitly on this idea of a choice function. Given a set, it picks an element out of the set. And so there's a whole branch of set theory called ZF and another branch called ZFC. And you get slightly different places depending on which one you follow. And this is weird, right? Like I say, if you want to Google that, it's an interesting area. It gets into things called Zorn's lemma and well ordering theorems and all kinds of stuff like that. And we're not going to use this in the class. I just want to mention it because we're leaving set theory for now. But it's a good kind of like parting shot on some of the strangeness around sets. All right, some of your final attendance ping, and I will see you next time. And we'll start talking about propositional logic on Wednesday. So that'll be our next unit. All right, have a good one.
Thank you.
Thank you.
You're welcome.
Have a great day.
Thanks, you too.